Hi to everyone, myself Dr. Dhananjay Rao, working as assistant professor in the Department of Chemistry. Today's topic is thermo response materials. Thermo response materials. In this session, I am going to cover thermo response materials, in that polyacrylamide and polyvinyl amide. I am going to explain about thermo response materials in that polyacrylamide and polyvinyl amide. See, thermo responsive materials, that is temperature responsive polymers. Temperature responsive polymers. These are the polymers that exhibit drastic and discontinuous changes in their physical properties with temperature. Okay, what is thermoresponsive materials? These are the polymers that exhibit drastic and discontinuous changes in their physical properties with temperature. These are the polymers that exhibit drastic or discontinuous changes in their physical properties of with a temperature. The thermoresponsive polymers are class of smart materials. This comes under smart materials. The thermoresponsive materials comes under smart materials that have the ability to respond to change in the temperature. Okay, these are having the responding property. These materials respond to the temperature. Okay, these properties will changes. A property that makes them useful materials in a wide range of applications and consequently attracts much scientific interest. A property that makes the useful materials in a wide range of applications and consequently attracts much scientific interest. The thermoresponsive polymers are the class of smart materials that have the ability to respond to a change in the temperature. Okay, these are change with the temperature. This property makes the useful material in the wide range of applications and consequently attracts the much scientific interest. See, these are the thermoresponsive materials. See, micelle, cross-linked micelle, covalently linked gel, okay, interpenetrating network, physical gel, polymerism, okay. See, these are the applications with thermoresponsive polymers. Drug delivery and gene delivery and tissue engineering. These are the applications of thermoresponsive polymers. There are two main types of thermoresponsive polymers are present. There are two types of thermoresponsive polymers are present. See, one is lower critical solution temperature, LCST. There are two main types of thermoresponsive polymers are there. And the first one is lower critical solution temperature based polymers, and the second one is upper critical solution temperature based. The lower critical solution temperature based and the second one is upper critical solution temperature based polymers. See, the lower critical solution temperature. The lower critical solution temperature. The lower critical solution temperature or LCST or lower consolute temperature is the critical temperature below which the components of mixture are miscible in all proportions. Okay. The lower critical solution temperature LCST or lower consolute temperature is the critical temperature below which the components of a mixture are miscible in all proportions. See, this is the LCST. Okay, that is lower critical solution temperature. Below this what happens? The mixture components are miscible in all proportions. These mixture components are miscible in all proportions. That is called LCST or lower critical solution temperature. The second one is upper critical solution temperature. Upper critical solution temperature. The upper critical solution temperature, okay, UCST or upper consolute temperature is the critical temperature above which the components of a mixture are miscible in all proportions. See, in UCST or upper critical solution temperature, okay, above which the components of a mixture are miscible in all proportions. See, this is the UCST, okay, upper critical solution temperature. Above this temperature, above upper critical solution temperature, the mixture of components are miscible in all proportions. These components of a mixture are in miscible state, okay, in all proportions. The LCST, below the LCST, the all components of a mixture are miscible in state, and above this UCST, same, all the components of mixture are in miscible state. In between LCST and UCST, the mixture components are exhibited in a miscible state. Okay. The LCST and UCST are the respective critical temperature points below and above which the polymers and solvents are completely miscible. The LCST and UCST are the respective critical temperatures points below and above which the polymers and solvents are completely miscible. See the miscible. I explained previously. Below this LCST and above this UCST. In between the LCST and UCST, the LCST and UCST are the respective critical temperatures points below and above. Okay, in between these, the polymers and the solvents are completely miscible. The solvents and the polymers are completely miscible. Okay. The example for the this thermo material is polyacrylamide. Thermo responsive material example is polyacrylamide. See, it's also briefly referred as PAM. Okay, polyacrylamide, nothing but PAM. Polyacrylamide. We can briefly referred as PAM. Is commonly a polymer with acrylamide monomers bonded connected by end-to-end configuration. How we can prepare? The acrylamide monomer is bonded connected by end configuration. See, this is the acrylamide CH2 double bond CH2 C double bond O NH2. This is the structure of the acrylamide. Okay, these are acrylamides are bonded to each other in end-to-end configuration. It is formed by the polymerization of free acrylamide monomer radical. Okay, it is formed by the polymerization of free acrylamide monomer radical. See, it is a hard glassy solid at room temperature. It is hard glassy solid at room temperature. See, the acrylamide, okay, it undergo free radical polymerization. The mechanism involved in this free radical polymerization. The catalyst is ammonium persulfate, NH4S2O8, NH4 taken to S2O8 at 50 to 60 degrees centigrade. Okay, the ammonium persulfate is a catalyst at temperature 50 to 60 degrees centigrade. The acrylamide undergo free radical polymerization. It will form polyacrylamide. See how we can prepare polyacrylamide. The polyacrylamide nothing but the monomer is acrylamide. The acrylamide monomer is undergo polymerization in the presence of the catalyst ammonium persulfate NH4 to S2O8 ammonium persulfate at the temperature 50 to 60 degree centigrade. It forms polyacrylamide. The polyacrylamide has both hydrophilic amido group and hydrophobic alkaline group. Okay, the structure of CH2 double bond CH2 C double bond O NH2. Okay, this is the taken by sen. This is the structure of PAM, polyacrylamide. It has both hydrophilic amide. See, this is the amide group is hydrophilic in nature. Hydrophilic. This is the hydrophilic functional group. Okay, it is hydrophilic and it contains hydrophobic alkene group. This is hydrophobic in nature. The alkene group is hydrophobic. Okay, the PAM consists both hydrophilic. The hydrophilic functional group is amide functional group is the amide functional group is the hydrophilic functional group, and the remaining alkene group is the hydrophobic alkene groups. When the temperature is low, okay, there is a strong hydrogen bond between the amide group and the external water molecule. Okay, see, if you this polyacrylamide. Okay, for this polyacrylamide, if we add water molecules, if we add to this polyacrylamide, at low temperature, what happens? This amide functional group forms a hydrogen bonding. C double bond O is there, NH2 is there. Okay, water nothing but OH. Okay, there is a hydrogen bonding between oxygen to hydrogen and nitrogen to this hydrogen. Okay, external water molecules. When the temperature is low, okay, in the low temperature condition, there is a strong hydrogen bond between the amide group and the external water molecules. Okay, the polyacrylamide is the hydrophilic. Macroscopically, swelling occurs for the volume. Okay, in the low temperature, what happens? These water molecules forms hydrogen bonding with this polyacrylamide at low temperature. So the swelling takes place. Okay, because of this hydrogen bonding at low temperature, the swelling of this polyacrylamide takes place. Okay, when the temperature reaches the low critical dissolution temperature, okay, when the LCST, when the temperature reaches the low critical dissolution temperature, the hydrogen bond between the amide group and the water molecule is destroyed. Okay, when applying this temperature, when the temperature reaches to the low critical dissolution temperature, the LCST reaches, the hydrogen bond between this amide group and the water molecule is destroyed. Okay, the hydrogen bond between this amide group and the water molecule is destroyed. The hydrophobicity of the alkyl group in the structure plays a leading role. In this case, the hydrophobicity means the alkene group present, the size of the alkene group present in this amide, polyacryl amide will the plays the leading role, and the PAM becomes hydrophobic and gradually shrinks. Okay, when the temperature reaches LCST, means low critical dissolution temperature reaches, okay, the hydrogen bonds between the amide group and water molecules destroys. Okay, because of the hydrogen bonding breakage, okay, the shrink will be takes place in the polyacryl amide due to the breakage of the hydrogen bonding. Many studies have shown that the LCST of PAM is about 32 degrees centigrade. Okay, many studies that shown the LCST of the PAM is about 32 degree centigrade. Okay, below this LCST, it means the 32 degree centigrade, there is no hydrogen bonding between this polyacryl amide and water molecules. The PM is in the shrink form, which is close to physiological temperature and easy to adjust. So it has been developed for biomedical, example, drug delivery systems, cardiovascular repair and sensing analysis, and medical imaging, and so on. Okay, because of this adjustment of this low temperature, we can adjust the 30 degrees centigrade. Okay, we can manage this temperature very easily. So which is close to the physiological temperature, it is close to our physiological temperature and easy to adjust. We can easily adjust this 32 degree centigrade. So it has been developed for the biomedical and drug delivery systems, cardiovascular repair and sensing analysis, and medical imaging, and so on. We can prepare by using this polyacryl amide at 32 degree centigrade. See, this is the hydrophilic above 32 degree centigrade. Okay, above 32 degree centigrade, it is hydrophilic in nature, means it is expandable. It forms hydrogen bonds with the water molecules. Okay, this exhibit hydrophilic in nature. Okay, below 32 degree centigrade. Okay, 32 degree centigrade is the LCST, lower critical solution temperature. Below this 32 degree centigrade, what happens? There is no hydrogen bonding between the water molecule and this PAM, polyacryl amide. So hydrophobic in nature. Okay, that this is in the shrink form. Okay, here the expandable form of the polyacryl amide. This is the shrink form of the polyacryl amide. See the properties of the polyacryl amide. The properties of the polyacryl amide. The polyacryl amide PAM is a water soluble synthetic polymer. It is a water soluble synthetic polymer which possesses a useful properties such as good adhesiveness, proper hygroscopicity and hygrophilicity, and non-toxicity. Polyacryl amide is a water soluble synthetic polymer which possesses a useful properties such as good adhesiveness and proper hygroscopicity and high hydrophilicity and non-toxicity. It has good thermal stability and is soluble in water. It has good thermal stability and it is soluble in water. Its aqueous solution is clear and transparent with its viscosity increasing with the increasing molecular weight of the polymer. Its aqueous solution is clear and transparent with its viscosity increasing with increasing molecular weight. With increasing molecular weight, its viscosity also increases in the polymers, and also having a logarithmic relationship with the change in the concentration of the polymer. It shows the logarithmic relationship with the change in the concentration of the polymer. Except for a few solvents such as acetic acid, acrylic acid, ethylene glycol, glycerol, and formamide, it is generally insoluble in organic solvents. Formamide, it is insoluble in organic solvent. Except for a few solvents such as acetic acid, acrylic acid, ethylene glycol, glycerol, and formamide, it is generally insoluble in all organic solvent. What are the properties of the polyacryl amide? See, the polyacryl amide is a water soluble synthetic polymer. It is a synthetic polymer and it is a water soluble which possesses useful properties such as good adhesiveness and proper hygroscopicity and high non-philicity and non-toxicity. It has good thermal stability and is soluble in water. It has a good thermal stability and it is soluble in water. Its aqueous solution is clear. Its aqueous solution is clear and transparent, with its viscosity increasing with increasing molecular weight. The molecular weight of this PAM is increased with the molecular weight, and also having logarithmic relationship with the change in the concentration of the polymer. It shows the logarithmic relationship with the change in the concentration. The viscosity of the logarithmic relationship with the change in the concentration of the polymer. Except for a few solvents such as acetic acid, acrylic acid, ethylene glycol, glycerin and formamide, it is generally insoluble in all the other organic solvents. The thermoresponsive property. See, the PAM is a well-known thermoresponsive polyacrylamide. The PAM is a well-known thermoresponsive polyacrylamide. It has a lower critical solution temperature LCST around 32 degrees centigrade. It contains the LCST, the lower critical solution temperature, that is 32 degrees centigrade. Below this temperature, PAM is water soluble and hydrophilic. Below this temperature, PAM acts as a hydrophilic and it is a soluble in organic. It is water soluble and fill in the form. Okay. Below this 32 degrees centigrade, what happens? There is a hydrogen bond formation takes place with the water molecule and the amide group present in the polyacryl amide below the LCST temperature, that is below the 32 degrees centigrade. Above this LCST 32 degrees centigrade, it becomes hydrophobic and undergoes phase transition, precipitating out of the solution. Above the LCST, okay, above the LCST 32 degrees centigrade, what happens? It is converted into the hydrophobic, and the phase transition occur. The hydrogen bonding breakage occur in the PAM and water molecule at above the LCST, and the precipitation will takes place. The applications of this, the polyacrylamide thermoresponsive material. The PAM and other polyacrylamides with similar thermoresponsive properties have applications in drug delivery, tissue engineering, and as a components in a smart materials. The PAM and other polyacrylamides with similar thermoresponsive properties have applications in the drug delivery, tissue engineering, and as components in a smart materials. The serum proteins must be adequately removed to prevent inhibition of the trypsin. Serum proteins must be adequately removed to prevent inhibition of the trypsin. If phenol present in the cell media, the polyacrylamide gel should be changed from pink color to the almost clear. If phenol present in the cell media, the polyacrylamide gel should change from pink color to the almost clear. Okay, indicating the cells are ready to be trypsinized. It indicates the cells are ready to trypsinize. Okay. The other uses of PAM, other uses of polyacrylamide. It is used as a flocculant in water treatment industry. It is used as a flocculant in the water treatment industry. It can be used as setting agent in sugar industry, settling agent. Okay, it can be used as a setting agent in a sugar industry and settling process. Okay, it can be used as a soil conditioner, flocculants, and it can be used in a textile industry. It can be used as soil conditioner and flocculants, and it can be used in the textile industry. It can be used at coal field and oil field. It can be used in the coal field and oil field. It can also be used as sewage treatment agent. It can also be used as sewage treatment agent. See, the other use of PAM, polyacrylamide, is it is used as a flocculant in water treatment industry. It is used as flocculant in water treatment industry. It can be used as setting agent in sugar industry and as a settling agent. It can be used as a soil conditioner, flocculants, and it can be used in textile industry. It can be used at coal field and oil field. It can also be used as sewage treatment agent. The next one is polyvinyl amide. This is also an example for the thermal responsive material. The amongst thermoresponsive polyvinyl amides, poly-N-vinyl lactoprolactam, PNVCl, the short form is PNVCl, is a well-studied temperature responsive polymer. It is a well-studied temperature responsive polymer. Second only to polynisopropyl acrylamide, PNI-PAM, and the most popular temperature responsive polymer. These are the most responsive thermopolymers. The polymers show similar LCST behavior in water between 30 to 30 degrees centigrade. Similarly, the polyacrylamide shows the 32 LCST is 32 degrees centigrade. Similarly, the polyvinylamide, the PVAM, the polyvinylamide also having the LCST temperature, the lower critical solution temperature, that is in between the 30 to 32 degree centigrade. See the preparation of the polyvinyl amide. Okay, see this is the amide lactam. Okay, this is the amide lactam in presence of, see, 3-mercaptopropanoic acid, in presence of 3-mercaptopropanoic acid, and the ABN as ibutyl nitrile, bis isobutyl nitrile, isobutyl nitrile, AIBN, azo isobutyl nitrile. See, and double bond, isobutyl, CH2 CH3 C triple bond and isobutyl. Okay, 1 2 3 4 isobutyl. Similarly, C triple bond CN and CH3 CH3. This is the structure of ABN, isobutyl nitrile, in the solvent dimethyl formamide at 70 degrees centigrade, and it undergo polymerization. Okay, it undergo polymerization, it forms polyvinyl amide. This is the lactam, polyamide lactam. Okay, it undergo polymerization with the 3-mercaptopropanoic acid in presence of ABN, isobutyl nitrile, See the structure of isobutyl nitrile is, azo means N double bond N, isobutyl CH3 C triple bond N. Similarly here also CH3 C triple bond N. This is the structure of ABN, isobutyl nitrile. This is the structure of 3-mercaptopropanoic acid. These two undergo polymerization, form polyvinyl amide, PVAM. The synthesis of PNVCl COOH polymers be free radical polymerization by using a modified version of the protocol. This is the modified free radical polymerization process. Okay, the properties of polyvinyl amide. The properties of the polyvinyl amide. See, able to thicken across a wide range of pH. Able to thicken across a wide range of pH. Able to thicken high salt concentration solution. Able to thicken high salt concentration solution. It resistance to acids and alkalis. Okay, it is resistance to the acids and alkalis. It is water soluble. And adhesion and pressure sensitive adhesion. Okay, it is adhesion and pressure sensitive adhesion. The resistant to heat, it contains resistant to heat. The polyvinyl amide properties like strength, thermostability, chemical resistance, transparency, lightweight, and moldability. Okay, these are the properties of the polyvinyl amide. The polyvinyl amide, the thermoresponsive property. Poly-N-vinyl caprolactam or PNVCl. Poly-N-vinyl caprolactam, the short form is PNVCl, is an example of the polyvinyl amide with the thermoresponsive behavior. Okay, it is also a thermoresponsive material. It exhibits similar LCST as a PNI form. Okay, it exhibits a similar LCST as a PNI form, making it soluble in water below the LCST and insoluble above it. Below this LCST temperature, it is also a water soluble. It forms a hydrogen bond with the water molecule, similarly like FAM. Okay, and above this LCST, it is insoluble. Okay, it breaks there is no bond formation between the water and this amide functional group. Applications of the polyvinyl amide. See, polyvinyl amides are used in various applications, including drug delivery as flocculants and in the formulation of the responsive coatings. These are having the applications in the industry, in drug delivery, flocculants, and it is the formulation of the responsive coatings. In both cases, the thermoresponsive behavior of these polymers allows for a controlled changes in their solubility, which is advantageous for the application of where the temperature dependent properties are desired. In both cases, okay, in about two materials, the thermoresponsive materials, the thermoresponsive behavior of these polymers allows for controlled changes in their solubility, which is advantageous for the applications where the temperature dependent properties are desired. Where the temperature dependent properties are desired, we have the advantages for the applications. These properties can be harnessed in drug delivery systems where the polymers can act as carrier that releases a payload in response to temperature changes, or in other smart material applications. These properties can be harnessed in drug delivery system where the polymers can act as a carrier that releases a payload in response to temperature changes or in other smart material applications. Additionally, the LCST of these polymers is often close to body temperature. These are having the LCST temperature of these polymers are often close to the body temperature, making them particularly suitable for biomedical applications. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.